It's not always possible to directly apply L'Hopital's rule. This is why we have second case. If you have infinity minus infinity or 0 times infinity case, then it means you have the second type for indeterminate forms of limits. So what can we do if we have this kind of limits? Let's look at this type of limits. First, limit when x tends to infinity, x minus ln x. As you see, when x tends to infinity, this part tends to infinity, and of course ln x tends to infinity. So you have infinity minus infinity case, and it means you cannot apply L'Hopital's rule directly. Right? So if you have 0 over 0 or infinity over infinity, then of course you can apply L'Hopital's rule. Otherwise you cannot. So in this case, what's your idea? I will suggest two ways to solve this problem. And the first way is, first substitute the expression x minus ln x. Let me take the parentheses of x. If you take the parentheses of x, you have 1 minus ln x over x, right? So in this case, when x tends to infinity, this part of course is infinity, and you have 1 here, and you have infinity over infinity again. So for infinity over infinity, you can apply L'Hopital's rule. Let's focus on this part here. Let's say we have the question limit of ln x divided by x, infinity, x tends to infinity. You have infinity over infinity. This is why you can apply L'Hopital's rule. Let's apply L'Hopital's rule. Derivative of ln x is 1 over x, and derivative of denominator is 1. When x tends to infinity, this expression becomes 1 over x. When x tends to infinity, this goes to 0. Right? So when you go back to the original question, what do you have? You have infinity times 1 minus 0. So the answer is, of course, infinity. Infinity times 1 is equal to infinity. It is the first way. What about the second way? What about the second way? This expression, you may say that this expression is equal to, instead of x, it's possible to write ln e to the power x, right? Using the properties of ln function. Ln e to the power x is x times ln e. Ln e is equal to 1, so x times 1, which is x, minus the second term itself, ln x, right? So using the properties of ln again, when x tends to infinity, you have ln numerator over denominator. Using the properties of limit, this expression becomes, you can take the limit to the inside of the parentheses, e to the power x divided by x. So what do you see when you look at this expression? E to the power x goes to infinity, x goes to infinity when x goes to infinity. So you have infinity over infinity case inside of the parentheses, right? So you have infinity over infinity. So it means you can apply L'Hopital's rule. Let's apply L'Hopital's rule to the inside of the parentheses. Derivative of course, we should not forget limit expression here. Derivative of e to the power x is the function itself, and derivative of denominator is 1. And when x tends to infinity, this expression goes to infinity, and when inside of ln goes to infinity, ln itself goes to infinity. So the answer is, of course, infinity. So if you have the second type, you may convert type 2 to type 1 to apply L'Hopital's rule, or you may manipulate the question itself and then try to solve the limit problems. So you have two ways to solve this kind of questions. Let me give another example. Limit when x tends to 1 over x minus 1 over ln x, minus 1 over x minus 1. Okay, so when x tends to 1, as you see, ln x tends to 0. So 1 over 0 tends to infinity. This part, the second part, is also going to infinity. So you have infinity minus infinity case. So it's called type 2. You have to convert type 2 to type 1 to use L'Hopital's rule. So let's convert. Let's try to convert. Let me first make the denominators equal to each other. X tends to 1. So if you make denominators equal to each other, then you have x minus 1 here minus ln x. I will not go to details. And the parentheses of x minus 1, you have ln x. When x tends to 1, as you see, numerator tends to 0, denominator tends to 0, so you have 0 over 0 case. It means you can apply L'Hopital's rule now. So let's apply L'Hopital's rule. This limit expression is equal to derivative of numerator, derivative of x is 1, derivative of 1 is 0, derivative of ln x is 1 over x, divided by derivative of denominator. If you compute, you will see that derivative of denominator is x minus 1 over x plus ln x. You have the multiplication of two functions. Do not forget the formula for the derivative of multiplication of two functions. Then, if you substitute this whole expression, you will have x minus 1 over x minus 1 plus x ln x. When x tends to 1, when x tends to 1, as you see, you have again 0 over 0 case. This is why we have to apply L'Hopital's rule again. Derivative of numerator is equal to 1. Derivative of denominator is equal to derivative of x is 1. Derivative of 1 is 0. And you have multiplication of two functions. Derivative of this expression is equal to, okay, derivative of first component times second, which is ln x. Derivative of ln x times x is 1. When x tends to 1, as you see, the answer is equal to 1 over 2. Okay, I think it's a nice question for type 2. I have a final example for this type of limit questions. The question is limit sine x, multiplication of sine x and ln x. X tends to 0 from right. When x tends to 0 from right, ln tends to 0. Sine tends to 0. And ln tends to infinity. What do we have here? We have 0 times infinity case, which is called type 2 case. We have to convert this type to type 1 to have L'Hopital's rule. So let's continue. This limit expression, let me first manipulate or substitute this expression as limit x tends to 0 from right ln x. Okay, it's possible to take sine x to the denominator. So how do we write? Sine x to the power minus 1. Okay, it's not arc, it's not inverse sine, it is 1 over sine. Okay, so it is 1 over sine. When x tends to infinity from right, again 1 over sine x goes to infinity. Okay, 1 over sine x goes to infinity, and ln x of course goes to infinity. Since you have infinity over infinity case, you can apply L'Hopital's rule. Let's apply. X tends to 0 from right. Derivative of numerator, derivative of ln x is 1 over x. Derivative of denominator is, you take minus here and reduce the power of minus 1. So you have 1. If you reduce, you have 2. Okay, and times derivative of inside, which is cosine x. Okay, let's first substitute this limit, this complicated limit expression. If you substitute, you will have, I take sine x to the power, to the numerator, sine x square. And you have x here. Of course, you also have cosine x here. Okay, and when x tends to 0, if you look at this expression, you have 0 over 0 again. But if you write this limit expression as, okay, let me write down here. I will do something else. If you write this, since I see sine x here and x here, okay, I prefer to write this expression as multiplication of two limit functions. Sine x over x here times limit x tends to 0 from right. What do we have? We have sine x divided by cosine x. When x tends to 0 from right, sine x over x, this part goes to 0 and this part goes to 1. This is why this multiplication goes to 0. Okay, so I will give type 2 in the next lecture.